One of the things that you might have been thinking about is when looking at the SN1 and SN2 reaction mechanisms is you can see they're both nucleophilic displacement, and for the most part they give essentially the same type of products. When is it that SN1 occurs and when is it that SN2 occurs? And so that's what we're going to look at right now. The first thing that you need to realize about SN1 and SN2 is that it is the characteristics of the substrate that now there are several different controlling factors for SN1 or SN2. There's the type of carbon or the substrate, the nucleophile, the leaving group, the solvent, and even the temperature, which we're not going to go into. The most important thing to consider when looking at a reaction and trying to determine does it go SN1 or does it go SN2 is to look at the type of carbon or the substrate that is reacting. When you have SN2 has a very crowded transition state. There are 5 things around the carbon in an SN2 reaction. You have the nucleophile coming in while the leaving group has not yet left. And then you've got 3 attachments on that carbon in addition to the leaving group and the nucleophile. This makes that transition state very crowded. As a result, unhindered carbons are more likely to undergo SN2 reaction than hindered carbons. So what you can derive from this is that methyl halides, because they only have hydrogens attached to the carbon, react very quickly. Primary carbons react very quickly because there's only 1 carbon attached and 2 hydrogens. Secondary carbons have 2 carbons attached, and you're beginning to get a pretty crowded transition state. They can react, but they can be slow. They can be so slow that they don't occur very quickly enough to be useful. Tertiary carbons are so crowded because there are 3 carbons attached to that carbon that they do not undergo SN2 reactions at all. And then, of course, you don't have nucleophilic displacement occurring at all on an sp2 carbon, so we don't have to worry about the vinyl halides at all. So keep in mind, what's fastest? Methyl. What's next fastest? Primary. What's next fastest? Secondary. And nothing else happens there. Tertiary never do SN2. With SN1 reactions, you have just the opposite effect. SN1 reactions are controlled by the stability of the carbocation. Because it has a carbocation intermediate, the stability of the carbocation influences the energy of the transition state. If you have a very high energy transition state, a very high energy carbocation, you're going to have a very high energy transition state. And if you have a low energy carbocation, then the transition state will be lower and the reaction will be faster. So let's look at this kind of thing. Tertiary halides will have a tertiary carbocation intermediate. So they undergo SN1 reactions very fast because their tertiary carbocation intermediate is not as high energy as the others. Secondary are slower. They still will go, but they do have a slower SN1 reaction than a tertiary halide. Primary halides are very slow in SN1 reactions. And they might react depending on the leaving group that's on there. Methyl carbocations are unreactive to SN1 reactions because a methyl carbocation has no stabilization from the alkyl groups attaching and undergoing hyperconjugation to stabilize the carbocation. And of course, we've seen that no nucleophilic displacement can occur on carbon-carbon double bonds because the carbon is sp2, and so there's no reaction at sp2 carbons. Note, we have seen that carbocations are stabilized by adjacent pi systems. So on any of these possible any of these possible substrates, tertiary, secondary, or primary, if you have a pi system adjacent to the carbon that's undergoing the nucleophilic displacement reaction, you will have a faster reaction. And so you can get primary carbons to react in SN1 reactions if you have a pi group. So why is there a rate difference in SN2? It's because of steric hindrance. Steric hindrance will slow down an SN2 reaction because it's a very crowded transition state. And so, if you have a tertiary carbon, you cannot get it to undergo SN2 because the 3 alkyl groups on that carbon just block the backside of that carbon from undergoing an SN2 reaction. Remember, we called it backside attach, and those alkyl groups are basically crowding around the backside of that tertiary carbon. An SN2 reaction on a secondary carbon is rather slow, but it will go ahead. It's just slow. If you have a primary carbon, there's no steric hindrance, or essentially no steric hindrance, and so it's very fast. SN1 reactions are controlled by the stability of the carbocation. So the more stable the carbocation, the faster the reaction. So tertiary, of course, are going to be very fast. Secondary are going to be next. And of course, methyl will be the absolute slowest, which is like not at all. Notice the allylic position or the benzylic position is activated. And in this instance, we're comparing primary, no pi system nearby, and primary with a pi system adjacent. These are as fast as the secondary. So if a secondary carbon has an allylic or benzylic attachment, then wow, it's going to be as fast as a tertiary. So you can see the pi system stabilizes the carbocation and increases the rate of an SN1 reaction. All right, carbocation stability causes SN1 reactions to be fast for tertiary carbons, allylic carbons, and benzylic carbons. SN1 is very slow for primary carbons and will not occur on methyl or vinylic carbons because the carbocation is so unstable. It's high energy and very slow to form a carbocation. Allylic, benzylic primary carbons are stabilized when they're carbocations, and they're unhindered in an SN2 reaction. When an SN2 reaction occurs and it has an allylic or benzylic group adjacent to that carbon, it's faster than if it were not allylic or benzylic. And the reason is that transition state is stabilized by the pi system. The del positive that arises in the transition state on that carbon is stabilized by the pi system, lowering the transition state energy. So what did you learn? Tertiary and secondary substrates react well in an SN1 reaction, and the allylic and benzylic attachments increase the rate of an SN1 reaction. Primary do not react well in SN1 unless they have allylic or benzylic attachments. Primary and secondary substrates react well in SN2, and the allylic and benzylic attachments increase the rate of SN2. Tertiary substrates do not react at all in SN2 reactions. So, now with what you know, what mechanism would you expect for each of these reactions? Well, if you look at this first reaction, you can see it's a primary substrate right there. That iodine is on a primary carbon. So what you would expect is a bromide's going to come in and displace the iodine and form this product. How will this reaction go? Since this is a primary carbon, it's going to go SN2. On this reaction, this is a tertiary carbon. What's going to happen? The bromide will leave, The water will come in and sit down on the carbocation and then lose a proton. As a result, we get the tertiary alcohol. And how do we expect it to go? Because it was a tertiary carbon, we expect an SN1 reaction. With this carbon, it's secondary, so it really could go either secondary, SN1 or SN2. Because there is this benzylic attachment, you will find that the carbocation is greatly stabilized. The steric hindrance remains the same, although the transition state is somewhat stabilized by the pi system. We see that the iodine will leave and the water come in as a nucleophile, then lose a proton, and we get this alcohol, and we expect that this reaction. What mechanism would you expect from these reactions? If I look at this carbon, you can see it's a deuterium and a hydrogen and then a propyl group on it. This is a primary carbon. Deuterium is nothing more than a hydrogen, no bigger. So this carbon is going to undergo an SN2 reaction. The iodide is going to come and displace the chlorine. The product is going to be inverted. Notice the inversion. And it will go by an SN2 reaction. Here, the bromide is going to leave, leaving a carbocation right here, a tertiary carbocation. The alcohol, oxygen, will come sit down on that carbon, and then it will lose a proton. The resulting compound is this alcohol ether. The ethanol attaches here. It lost its proton. And what we get is an SN1 mechanism. Why? Because it was tertiary.